We have a habit of looking at modern civilization and giving science all the credit. We uncover the chaotic secrets of the universe, and we assume human progress automatically follows. Knowing a uranium atom splits doesn't assemble a nuclear reactor. Charting a virus's molecular structure doesn't magically produce a vaccine. Raw scientific knowledge is entirely passive. It is simply observation. To the average person, a complex physics equation is completely useless until someone forces that math into a physical, workable solution. That physical translation, turning abstract mathematics into tangible steel and silicon, is the discipline of engineering. The distinction is a matter of philosophy. Scientists exist to ask why. They look at the natural world and try to understand the rules governing its behavior. Engineers look at those exact same rules and ask how. How can we manipulate gravity, thermodynamics, or fluid dynamics to solve a specific human crisis? They rely on the engineering design process. This framework funnels theoretical inputs through testing, prototyping, and refinement until an applied solution emerges. Without this translation, humanity would sit in the dirt observing the universe, instead of actively constructing our civilization. Unlike theoretical science, which exists perfectly on a chalkboard, engineering must survive the punishing constraints of the real world. Every design must navigate the unyielding limits of gravity, materials, strict budgets, and human safety. The ancient Romans turned the principles of hydrology into continent-spanning delivery systems, moving millions of gallons of water over miles of uneven terrain to sustain entire cities. Fast forward to the Industrial Revolution, where physical inefficiency was the enemy of progress. Early steam-powered ships struggled with severe propulsion problems, wasting fuel and suffering from violent, destructive vibrations. It took a self-taught engineer named Henrietta van Settetart to attack this specific mechanical constraint. She studied the physics of water displacement and realized the standard propeller designs were fighting the ocean instead of cutting through it. Her physical solution was the low van Settetart screw propeller. By precisely curving the blades, she optimized the ship's speed, eliminated the destructive vibrations, and improved steering, all within the strict limitations of Victorian-era metallurgy. Having a brilliant concept is only the first step. An engineer's true genius lies in forcing that concept to survive the brutal, unforgiving limitations of physical reality. When the stakes escalate to warfare, this ability to problem-solve dictates the survival of nations. In aerial combat, engineering superiority determines who controls the sky. During the Battle of Britain, Royal Air Force pilots faced a deadly physics crisis. When their Spitfires and Hurricanes entered steep -G nosedives, the fuel flow to their massive Merlin engines would stall, leaving them powerless and vulnerable to enemy fire. Aeronautical engineer Beatrice Schilling solved the fuel starvation crisis by designing a specific restrictor valve, a simple piece of hardware that regulated flow and kept the engines firing through extreme maneuvers. In moments of existential threat, understanding the laws of physics isn't enough. Survival depends entirely on an engineer's ability to physically outmaneuver them. As human problems have grown infinitely more complex, the engineering toolkit has been forced to adapt. We have moved far beyond tangible steel and concrete. Software and systems engineers now construct vast digital infrastructures, optimizing the invisible networks that route our global data. To solve modern material crises, nanotechnology engineers manipulate raw matter at the microscopic scale, building structures out of single strings of atoms. Even the human body has become a design constraint. Biomedical engineers are currently mapping neural interfaces and designing advanced prosthetics that integrate directly with our biology. And at the absolute frontier, quantum engineers are harnessing the erratic behavior of subatomic particles to build computers that can process impossibly complex algorithms. But whether the tool is a massive stone block spanning a river or an invisible qubit processing cryptography, the identity of the professional remains exactly the same. They are the architects of how. This immense capability carries a heavy ethical burden. There is a sharp dividing line between a reckless inventor prototyping a new gadget and a rigorous engineer building public works. Every time you cross a bridge, undergo an MRI, or board a commercial flight, you are blindly trusting the math and materials selected by a stranger. Engineers serve as the ultimate guardians of this public safety. This silent public trust is what allows cities to function. We live in a world of calculated risks, and those risks only remain manageable as long as the engineer's professional integrity holds firm. As we look toward the next decade, humanity faces three massive existential threats: catastrophic climate change, global health crises, and the silent war of cyber attacks. Political rhetoric will not halt a rising ocean, and pure scientific observation will not inherently clean the atmosphere. It will take renewable energy engineers, tasked with rebuilding the global power grid to harvest wind and solar power at industrial scale. It will require environmental engineers designing sustainable ecosystems and data scientists deploying advanced algorithms to prevent the collapse of our digital infrastructure. Science will always define the exact parameters of the threats we face, but it is exclusively engineers who will build our way.